Well, hello all. Today we're going to have some fun finding the internal resistance of a battery or a cell. And we're going to be following this worksheet which has been prescribed by the department. It says here by the Cape Academy of Mathematics, Science and Technology. And I will put the circuit and this practical, I'll show you a close-up PDF version of it.
Right, so the Cape Academy of Mathematics, Science and Technology have this practical to determine the internal resistance of a battery by investigating the relationship between potential difference voltage across a variable resistor and the current I in the variable resistor. Aim to determine a battery's internal resistance. So that's what the whole thing's supposed to be about, but let's have a look. There's the circuit. Got a voltmeter, a battery, an ammeter, a variable resistor. That shouldn't be there, and it's also got a switch, but it does not have a second resistor. You'll see there's no mention of a second resistor there. Method, they tell us to get at least 4 sets of current and potential difference readings by changing the variable resistor, and measuring the volts and the amps on each new setting. Then they give, for example, those sets of readings of current and amperage with different resistor settings. Questions, part 1. What quantity does the voltmeter measure when the switch is closed? What quantity does the voltmeter measure when the switch is open? For this investigation, write down the independent variable, the dependent variable. Use the data collected to calculate algebraically using a formula the EMF of the battery and the internal resistance of the battery. That's for 4 marks. It's probably the only question that's worthwhile. Well, there are a few others that are quite good, but this is supposedly the highlight of the prac, which is, do you see anywhere here where it's asking you to find the internal resistance except here? So for 4 marks here it asks you to find the internal resistance of the battery. Draw a graph of potential difference on the y-axis and current on the x-axis. What physical quantity is given by the y-intercept on the graph? What physical quantity is given by the gradient of the graph? Calculate the gradient of the graph. And then list 2 factors that would contribute to any inaccuracies in the results. 26 marks for that. You see, not much is on internal resistance.
So now we're going to get a battery. So we could use this battery, that's 9 volts, but we're going to use this battery, that's 9 volts. Look, we know it's 9 volts because it says it's 9 volts. And then if you look at the top, it's got this here which says positive, and it's got that there which says negative. Now normally with 9 volts, it's not going to give you a shock, but let's see. Oh, just joking. 9 volts can't give you a shock. Only way it can give you a shock is if you put your tongue across it. I'm not sure if this one would give you a shock if you put your tongue across it. I know that this little guy is probably going to give a shock. But you know, how hygienic is it with the coronavirus to be sticking your tongue? Ooh, that's quite a buzz. So I'm sure this is perfectly healthy. It's probably made in China. Perfectly fine. I don't want to lick this. I don't know where that one's been. So I don't know whether that would give me the same buzz if I had to try and test it. So we've got our cell or our battery. We need a few connectors. Yeah, we've got a multimeter in case we need to measure anything. Multimeter can measure current, voltage, resistance. Okay, so here's all our connectors. We've got some red ones, we've got some green ones, red ones and black ones. The red we attach more to the positive side of the battery. So for example, there where it says positive, we might attach that to the positive side of the battery, and then we attach the black ones. Don't have to. Nothing telling us we have to. The black ones we attach to the negative side of the battery. I wonder if this one would give me a bit of a buzz. Hey, but I don't know where these cables have been, so let's just give it a bit of a clean. I know where my shirt has been. Let's just see. There is definitely a bit of a buzz, but not much. I'm not recommending you all now go licking the crocodile clips. If I was Johnny Knoxville, I would probably attach the crocodile clips to my tongue, but I'm not a jackass. Okay, so now we need one of these bad boys. See, it's got a V on it. What do you think a V stands for? It's a what meter? It's a voltmeter, spelled M-E-T-E-R, a voltmeter. So it's got a black terminal, black, goes to our black wire. You can just clip it over the top into the metallic part there. And then it's got a red terminal. So now this is a 9-volt battery and it says -3. We attach that to the 3. We're going to send this voltmeter into paroxysms. It's going to, the little thing is going to go right past the end. So we're going to go for 15, and then it's got also can do 300 volts DC. It's a DC meter, and we've got a DC voltage. So let's put it on the 15, and let's see what it reads. Now, do you see on the 15, we're reading on the top one. So there's 5, 10, 15, and we see that every 2 units is going to be 1 increase in volts. So that's 2. So we see it's 2 from the end. So that is actually just a fraction under 9 volts. It's about 8.9. It's about 8.9 volts. So it is almost a 9-volt battery. So now what we are measuring at the moment with no external circuit, just with a voltmeter attached to the battery, is we measuring the maximum voltage when no current flows. Now, what is that called? The maximum voltage when no current flows. Now, another thing you have to know is the only current that is flowing is moving that little needle. This voltmeter's got big or small resistance if no current flows. It's got a massive resistance, infinite resistance. Well, we talk about a very big resistance as being infinite, but we know that it's got almost infinite resistance, so that it's not flattening the battery. This is not a short circuit at the moment. If we were to stick an ammeter like this, now an ammeter's got no resistance. We don't say no, we say neglige. No, not neglige, negligible resistance. So an ammeter's got negligible, meaning very little resistance, and a voltmeter's got infinite, meaning or very high resistance. You can say that it is infinite. It's almost like having air between these clips. It's not going to change the voltage or the EMF. So now at the moment we are measuring the EMF as 8.9 volts. That's the maximum. You can't get any higher because of the chemicals in the battery. That's as much as they can push out. That is their top voltage, and that is limited by the chemicals in the battery. Now this battery is probably a little bit flat. I'm sure when it was new it was a little bit above 9, as most batteries are. They're above what they sell them as. But it's been used a long time, and it's now 8.9. Okay, so we must make sure we can read a voltmeter. Then they ask us to set up that circuit. So that circuit has got a voltmeter across a battery. Then it says it goes to a switch. So let's take from the negative, it goes to a switch. So here we go. Now you follow it as the circuit diagram goes. So it says from the negative, that's that short stroke, it goes to a switch. Okay, we don't have another, whoops, that's a red one, I'm colorblind. I wanted a black on black. This is black to negative. There's a lead. Then we need another black one that's going to serve as our switch. I'm going to leave it open for the moment. And that goes to our ammeter. So now which side of the ammeter does it attach to? Well, it attaches, this is going to the negative side. We've just come from the negative side of our battery. So this now goes to the negative side of the ammeter. Then from the other side of the ammeter, it goes to a variable resistance. So we've got a variable resistance here. Look, it's something that's got 1, 2, 3. The middle's the sweeper, and then it's got, you can sweep from a minimum to a maximum by turning this little dial. It's lost its knob, so we're going to attach one crocodile clip there and one crocodile clip there, and this is our variable resistor. I tested it out. It goes from 0 to 11 ohms. So again, we're going to take a black lead. Have I got a black lead? Let me get another black lead. Right. So from here, we go from our ammeter. Now, our ammeter's got negligible resistance. I'm going to put it on the maximum, which is 5 amps, and I'm going to take it to the middle. It doesn't matter which one I take it, to the middle. And from the other side of this resistance, I'm now going to start using red leads. So then the red lead goes from the variable resistor to, so we've got one variable resistor, and then we're going to go straight back to the long side of the battery, which is the positive side of the battery. So from here, our positive wire goes to the positive side of the battery. So let's just try and organize this so that you can see it. Okay, so I'm going to just show the circuit. So there we're going. From the negative side of the battery, it goes to a switch, which I haven't closed yet. Then it goes to the negative side of the ammeter. Then it goes through our variable resistor, which is a 10 ohm resistor, it says. 10 ohms. So it goes from 0 to 10 ohms. Goes then back to the battery, and at all times we can measure our voltage. So all that's left for us to do is to close the switch. So let's just close the switch, and you will see our ammeter is measuring something. Now our ammeter is set on 5 amps, so we're measuring along the bottom scale there. 5 amps. We always choose the maximum because we don't know. And I don't know if you can, hope you can see it, but there is where the needle of the ammeter is. There's the needle of the ammeter. It's gone there. It's sinking a little bit. It seems to be sinking as we speak. So I'm going to get the minimum current first. Just turn the variable resistor, and you see the current goes up. So when I put it onto its least setting, which is like when the current is as close to 0 as possible, this is now going to be my first reading. So if there is 1, each of those small units, look how many divisions there are between 0 and 1. There's only 5 divisions. So each of those units must be 0.2 of an amp. So it's measuring 0.2, 0.4, 0.6, 0.7 amps. 0.7 of an amp. That is our first reading. So amps. 0.7, and let's go and have a look what our voltage says at the same time. Our voltage says, so that's 6.5 volts. Okay, so we make a note of the voltage. 6,5 volts when the current is 0.3. Now let's again dial up let's change the reading by changing our variable resistor. Let's dial it, we can change it right onto 2 amps. Do you see how that needle is now sitting on 2 amps? Let's see, so let's write that down, 2 amps, and let's see what our voltage is sitting at. Now, there's our voltage. Remember, we're reading it on the top, and each of 2 units is 1 volt, so it's going to be 1, 2, 3 volts, exactly, 3 volts. Okay, 2 amps, 3 volts. Let's change this again and see if we can get it any higher. Oh yes, we can go higher. There. Now just look at that, what the ammeter is reading. It's measuring 2,8 amps. Remember, each unit is 0.2, 2,8 amps. 2,8 amps. And look what the voltage has done. Wow. The voltage has gone down to half a volt. So that is half a volt. 0.5 volts. And let's just see if there's anything more we can do. So let's just get one more reading somewhere in between. Let's get it to 1.5 amps. 1,5 amps. And the voltage would be, look at that, it's going to be 1, 2, 3.5 volts. 3.5 volts. Okay, 3,5 volts. So now we've got our readings. One last thing which I'd like to show you is what happens when we simply take out our resistor and we just short circuit it. So we're going to have it where we get rid of our resistor. I think we just get rid of the resistor completely. There, we're taking out the resistor. And now we're going to get maximum current, minimum voltage. I just want to see what we get. So there, I've hooked it together. Look at the voltage is 0.5 volt. And the current is 0.5 volt. And the current is 3 amps. 0.5 volt, 3 amps. 3 amps, 0.5 volts. Three amps, 0.5 volts. Okay, now we must disconnect everything, or we're going to short circuit our battery completely. That was a short circuit. Look what's happened to the voltage. It's come down from 8.9 to 7.3. It's now 7.3 volts. And our original voltage, our EMF, was originally 8,9. But now our EMF, or maximum voltage, has gone down to 7.3 volts. Just have a look then at our table. There's our amps, there's our volts. When we had 0.7 amps, we had 6.5 volts. When we had 2 amps, we had 3 volts. When we had 2.8 amps, we had 0.5 volts. When we had 1.5 amps, we had 3.5 volts. And when we had 3 amps, we had 0.5 volts. So I guess that must be correct. So now we've just got to plot a graph of this stuff. Okay, do you see how easy it was relatively to get our readings? Let's hope we took our readings and measurements correctly. Let's draw a graph. Right, so here is our graph of voltage versus current as the resistor's external resistance value varies. We've plotted, draw a graph of potential difference on the y-axis. So there we've got our voltage or potential difference. We could write there potential difference or voltage on the y-axis. You see we've got both of our noughts. We know nothing goes below, so we can use both of our noughts. We've got the current in amps on the x-axis. We've made our various plots from our data. We've got the best fit line. You'll see all the dots seem to form a more or less straight line. So we've got one dot or one plot on the above there, and we've got one below the line. So we've got quite, I think, a good spread. So now, just have a look. We made to fit this graph, to fit this onto our graph paper, we had to make, for the voltage, we had to make every little new line is 0.2 of a volt. So we've only got 5 intervals between 0 and 1, and 5 between 1 and 2. So each interval is 0.2 of a volt. So if we now go and look where this graph intersects, we see that there's 0.2, 0.4, so it's going to be 8,4 volts, where that line, the line intercepts the naught axis, when there is going to be a maximum voltage when there is a minimum of current. Look at that relationship between volts and amps. As the current rises, the voltage falls. So we start with no current, big voltage. What do we call that voltage? The maximum voltage that we can get at any time when there's zero current? Well, you know the name for it. And then watch as it falls. It's falling in voltage as our resistance gets less. So there would be the point where there's zero resistance, maximum current that flows. Zero resistance would mean maximum current, but it also means least voltage. Let's read it. Now, each of these intervals is 0.1 of an amp. So this is going to be 3,1 amps is where it intersects the 0 volts axis. 3,1 amps. So we've got 8,4 volts maximum, 3,1 amps maximum, and that is when our external resistor, which was this thing, was turned all the way to one side, and that meant that it had 0 resistance. So there is our plot, and then we've got to answer the questions that are on the graph. What physical quantity is given by the y-intercept on the graph? What is that voltage there called? What physical quantity is given by the gradient of the graph? Now, the gradient of the graph is change of v over change of I. I say that they don't know what they're talking about when they ask what physical quantity is given by the gradient of the graph. I know what they think they're asking, but they don't. They're actually wrong in asking that. They have no clue what the physical quantity is given by the gradient of the graph. But anyway, do your best. Calculate the gradient of the graph. Now, you know how to calculate the gradient of the graph. You take the change of volts over the change of current. And remember, change is always final volts minus initial volts over final current over initial current. So it's always the final one. So this is going to be, for any slope of a graph, we're going to take the finals there. There's the initial part of the slope. So it's going to be those values are the final ones, those are the initial ones. So there's your initial volts, which is going to be here, and there's going to be, and then you end up with your final part of the curve, going from left to right. Calculate the gradient of the graph. So there we've done that. Let's see what the next question is. List 2 factors that would contribute to any inaccuracy in the results. Well, I don't know if you know it, but if a resistor gets a very high current through it, it gets hot. And the hotter it gets, the more resistance it gets. So we've got to keep the temperature the same. So as the current increases, this thing gets hotter and hotter. It's almost impossible to keep this at a constant temperature. So that would be it. I don't think the wires would get hot because always the voltage is dropped and the energy is lost across the resistance. And this is the only place where there's any resistance. Perhaps another thing that might contribute to it is the resistance of our ammeter. Now, ammeters are supposed to have no or negligible resistance, but maybe it's got some resistance. In fact, they do have a slight bit of resistance.